So, our second last section, Stokes' theorem. Well, Stokes' theorem has certainly got a lot going on for it. Essentially, it's a way to find one of these line integrals. That should have a C on it. And what Stokes discovered was that this single line integral can be converted into a surface integral, a double integral, surface integral, this guy here. And then this guy in turn can then be converted into this guy down here. And so essentially what we are looking at is a method that allows us to find a line integral, FDR. And the reason we kind of need such a really convoluted way around the problem is that there are many cases where this line integral is either impossible to do or so impractical it's not worth trying to do. So let's try and show you a little bit about the theory behind what's going on here. So imagine that you've got this curve. This is this guy here floating in space, in 3D space, curve C. And attached to it, there's this surface here. And this is the boundary of the surface. So imagine my hand's a surface. Here is the boundary, right? And if you project this down, think of it as like a light bulb, and you project a shadow on the ground, on the XY plane, you'll find region D. So region D is the projection of this surface onto the XY plane. And the curve C is the boundary, essentially like the edge of this shadow, but what it would be up in here. And this is a 3D curve. And this funny peanut thing is meant to be a surface going like this. But hard to draw, but it's the best I could do in 2D. So you need to know the equation of the surface to be able to answer this question. And we tend to call it g of xy. So z will be things like x squared plus y squared and so on. And the reason we need to know what the equation of the surface is because it goes here and here, right? We're going to differentiate with x and y. And so you might end up with a surface equal to z equals x squared plus y squared, which would basically be a big curve. We also eventually, as you'll find out, need to find the region D, that's a shadow on the XY plane, and we need to find it, and we need to be able to give the limits of integration of it. So that shape there would be horrible to do, but most of the time, the shape for the region D is going to be one that you're comfortable with, mostly triangles or parts or whole circles. And the reason we need to know that guy is because this double integral will be using this region here. So it might be x goes from 1 to 2 and y goes from x to x squared, or whatever it might be. And then we have this fella here. And P, Q, and R are the curl of vector field F. And the partial derivative dg and x by dg and y is back to this guy. It's the partial derivative of the surface. So you put this whole package together, and what it allows you to do is to find what is pretty innocuous looking, a little simple one-dimensional line curve. But the equation of that line curve is just too difficult to do in the automatic way. So we kind of do this roundabout sideways to finally get it. Let's jump right in and start with our first example then. And this is basically a version of question 1. All of them mention use Stokes' theorem, I think, except the last question. And that's helpful, but you probably would, when you see the situation, you kind of know that you have to go that way. So you're being asked to find this, which is true for all of the questions in this section. And you're told what the curve C is, right? So you're told what this guy is, and it's actually the line joining these 3 points in 3D space. So imagine a triangle in 3D space, that's representing the curve C. And here is your vector field F. So the job's essentially split into 4 main steps. So this is the order I'm going to do all these questions. Step one, if it's needed, because sometimes they tell you what the surface is. They just said z equals x squared plus y squared, in which case you don't need to find it. But in this case, we do. And what do we know about this surface z? Well, it's built from this triangle, but it's actually a little bit more than that. It's actually the plane passing through these three guys. And if you go through the entire process and you want to find the equation of a plane joining 3 points together, you would find, let's call that P and Q. You'd find P and R. You do the cross product of PQ with PR, and you then use the general equation that the normal times XYZ is equal to the normal times the position vector, let's say that guy. And can you trust me that after all that work, you get this equation? So x plus y plus z equals 3 is essentially the equation of a plane that passes through these points. So this triangle is only part of the story. The whole thing is a plane going like this. But those triangles are also important for step 2. Oh, by the way, when you get the equation of the plane z equals, in this case, 3 take away x, take away y, and we got that by just rearranging this guy to the form z equals. This equation is your g of xy that you'll be using later. Okay. Any questions so far? Okay. That's step 1 done. Step 1 is essentially find the equation for the plane, or the surface. It may not always be a plane. Now, if you imagine this shape here, this triangle, the 3 points that they gave us, the guy on the floor is this guy down here. That's D. That's region D. So step 2 is to find that region D and to get the limits of integration that we generated. Well, if you look at my little, I guess I should stop moving this guy around. If you look at the floor, do you see it goes origin 3 and 3? So origin 3 and 3 looks like that. Here's my x-axis. Here's my y-axis. If you find the equation going through these 2 points, the slope is -1, and it passes through the y-axis at 3, so that's where that came from. And x scans the usual vertical from 0 to 3. So that is the limits of integration for region D. So I've described region D now. The third piece of the puzzle is you now need to find the curl of F. And the reason you need to find the curl of F is because you need this guy, who eventually is going to help you get this guy. Well, what is the curl of F? Well, remember those guys? Ijk, the operator for delta, and this, and this corresponds to the vector field here. So that's where these guys came from. X plus y squared, y plus z squared, z plus x squared. And if you cover that guy up and you do major takeaway minor, major takeaway minor, major takeaway minor, you eventually end up with -2z, -2x, -2y. And we call, this is the curl F, but we call this guy P, this guy Q, and this guy R. And that's going to be important when we get to the final step, because our final step's coming up right now. The last and final step is to actually calculate this line integral. And we've got all the pieces. See, this is region D, there's its limits of integration. The formula has a -p of this, a -q of that, plus an R. So let's see where all the pieces come from. -p is that guy, so it's the negative of -2z, and then the derivative dg by dx comes from differentiating this guy. And if you differentiate him, where did that come from? Does that say -1? Oh, because I'm looking at the wrong guy. There we go. There we are. -1 comes from here. So let's do it again. So many pages here, I'm not sure I can do all of it at once. Negative p is negative of -2z. dg by dx is the derivative of this guy with respect to x. That's where the -1 came from. Negative q is the negative of this guy, -2x, times this partial derivative, which is -1. And then you have plus r, which is plus this guy. Okay, that all the pieces. Now, if you multiply these out and combine them, you get to there. And sometimes, probably more often than you'd like, there's a z floating around. And at this point, I'm going to replace the z by 3 minus x minus y. And the reason I can do that is because z is equal to, it's the same thing as g of xy, but z is equal to this guy. So this z gets replaced here. And then at this point, we've really just got a good old-fashioned double integral. Multiply all this out. Oh, almost everything cancels, and you get left with -6. And if you do this guy a couple of lines from now, at least you'll get -27. Let me take you through the 4 steps. There's your original question. Step 1 was to find the equation of the plane, and we did that. We got this guy here, which you rearrange as z equals. So that was step 1. Step 2 was to find out what this region looks like when you project it onto the floor. And that region we call the one that's on the floor, we call that D, and this is the limits of integration for that. Step 3, find the curl of F. This here represents the components of F. There's your operator. After a little bit of work, you get these 3 guys. This one's P, this one's Q, this one's R. And then finally, step 4, where you put all the information that you've got into one package. Here is your limit of integration for D. Here is the P, Q, and R that represents your curl of F. And here's your 2 partial derivatives that you use, and all of them, eventually, once you convert everybody into X's and Y's, and then integrate, you get -27. So that's about a 15-minute question. I was going pretty quickly. Probably take you a lot longer when you have to write as many of those steps as you need down. How are we doing? Any issues, any questions? Okay, let's move on to question 2 then. Find this line integral using Stokes' theorem. In this question, it's a plane again, but at least they told us the equation of it. And here is our vector field. Not only did they tell us the equation of the plane that's going to represent the surface, they also mentioned that it's in the first octant. Now, if you take the equation of the plane but rearrange it in the form z equals, you get this guy. So this represents our equation of our surface, the g of xy that we'll use later when we do the partial derivatives. Now, the next thing is I need to know, what does this guy here, what does he look like when you project him onto the floor? Well, if you take this equation, you get it crosses the z-axis at 1. You cover these up, it crosses the y-axis at half. And if you cover this up, it crosses the x-axis at a third. So z-axis at 1, y-axis at half, x-axis at a third. And if you reorientate it like this, what you now are looking at is basically a little triangle, this one here. And I'm doing the vertical version that goes like this. So that's why x goes from 0 to a third. I found the equation of that line in the usual way. It's slightly ugly, it's equal to this. And so the rectangle is 0 up to the straight line, 0 up to the equation of the straight line. And that takes us through our second part of the job, where we set up the limits of integration. I'm going to have to hide pages. I've got too many of these are all looking the same. Move over. Now we're on to step 3. Find the curl of f. Here is f. So 1, that guy, and this guy. If you do cover that guy up, for instance, this partial derivative just gets you x because the other term doesn't matter. This direction here just gets you y. So it's x take away y, which is this guy. If you were doing the last one, which is this fella here, this partial derivative with respect to x gets you 1. This gets you nothing. So 1 take away 0 gets you 1. And that's probably the most straightforward bit, is finding the curl, right? Because you're told f, right? And getting the curl is automatic from there. Now, once you do get the curl, remember that this guy represents p in our formula. This piece is q, and this piece here is r. So when we put all that information together, this here represents d, right? The limits of integration that generate d. There's the generic formula that they all use. And then if you put in p, which is this fella, it's a negative of this fella times dg by dy. And if you, dg by dx, I should say. And that guy gets you just -3. This guy gets you -2. And r is just 1. And if you multiply this all out and collect some terms, you probably could do a little bit more detail on that. Here is a pretty straightforward double integral, and the answer would be 1/24th when you're finished. So, step 1, find equation of the surface, z equals. Step 2, find what the floor looks like. So when the surface hits the ground, the xy plane, what does the floor look like? And find the limits of region D, which is what we call the floor in terms of x and y. Get the curl, then put the whole package together. And if things work out, you should get a pretty decent integral that you can do. It certainly would be a lot nicer than the integral you'd have to deal with if you didn't do it that way. In fact, in a lot of cases, I don't even think it's possible to do it that way. Do we have a question? Everything good? Okay. This is my feeble attempt at drawing a 3D picture. This red curve here, so it goes from here, goes to here, and back down to here. That's the curve C that they're talking about here. And they tell you, thank goodness, because I wouldn't want to figure it out. They tell us that this surface S has this equation. So we're good. So actually step 1 wasn't necessary because I know what the equation of the surface is. So can you imagine this being a surface? And it's pretty clear that it's in the first octant. So how do we find the floor, right? This region here, what does it look like? Well, the XY plane, the floor, makes Z equals 0. So if you go here and you make Z equals 0, you get that. And if you rearrange that, you get a circle. And since I know it is in the first quadrant, just looking at the picture, you can tell it's in the first quadrant. That's how I know. What I'm really looking at is 1/4 of a circle. So whenever you're doing an integral and it's got something to do with a circle as it has here, you know you're going to go polar. I mean, it just makes sense to go that direction. So in this case here, the region D is going to be in terms of r and theta. R is from 0 to 1 because that's the radius. And since you're starting here and curving to there, theta goes from 0 to pi upon 2. So that's region 2 taken care of. So I got my equation on my surface, check. I've got the limits of integration that generate the floor, the region D, check. 2 more things to do. Find a gradient, which is pretty straightforward, and then put the package together. Right, so here we go. Find the curl, I should say. Here's the curl of f, I k, the operator delta, and this guy is f. This guy here, right, comes from f, and this guy here comes from f. And if we do the usual cover me up, for instance, this one here, it's 0, take away y, and that becomes negative y. And the same thing happens here and happens here. If you're thinking about using this, what you would probably want to do is just go when the video is available and just freeze frame it on, you know, a page like this perhaps, or whatever point of the process you need to catch up on if you're unsure about one of the steps. So we've calculated these three guys that make up the curl, and it ends up simplifying to this guy, and this guy. So far, so good. Right, step 4. Here is the equation that will allow us to get that line integral. It's a double root integral over the region D of this expression. And D, right now, dy and dx, but later on, we're going to go polar on it. So you replace this guy here, P. So this guy here is him, minus in front of it. And dg by dx is this guy differentiated with respect to x. There's the middle guy. This is differentiated with y. And that's the last guy, which is just add r. And you put all that together, you get this. And everybody has to be an x and a y right now. So that z ends up getting replaced by this z here. And then at this point, I've cut a lot of corners. Essentially, the limit of integration in terms of r and theta. Every x and y that you see here, here, and here is turned into an r cos theta for the x's, and r sine theta for the y's. This guy x is the r cos theta. You can see this yr is the, you know, the r sine theta. The only one that's half decent is that this becomes 1 minus r squared. And you're going to have to trust me, because this big horrible mess turns into essentially 3 separate integrals. And if you separate them into 3 separate integrals, you actually can solve a lot of your work. Not completely, but you can reduce it. For instance, if I do that guy there, if I pull out a negative 2r squared, right, or just a negative r squared actually would be better, and then the other guy can get the 2 sine theta cosine theta, that will turn into the sine of 2 theta, and that guy there is negative 2 r squared. If you're doing the middle one, that's this guy here, variable separable. And if you're doing that guy at the end, also variable separable. By the way, all of them get an extra r, but that doesn't change anything I said in the process. And believe it or not, it's a negative answer. Usual. Any puzzles, any questions? How did you get from line 3 to line 4? Anything not make sense? Okay. There are altogether 7 questions. To varying degrees, I'm going over 6 of them. One of them I've just totally skipped out because, well, actually I could skip out a couple of these, but I want to try and give you as many examples as I can, and reduce the workload a little bit for you. Okay, so this is our vector field. The curve C is described as the intersection of this plane meeting up with this cylinder. So if you could imagine a cylinder, an infinite cylinder would look like this. And this cylinder has the equation x squared plus y squared equals 1. And it's meeting up with a plane, which is probably some kind of diagonal, whatever. And when these two things intersect, you have to trust me, you tend to get an ellipse. So that ellipse would be our center, but we already know what the equation that we're going to use. We already have a z equals, so that's our guy. So the surface is simply just that plane. Z equals y plus x. Now, how about what does the region on the floor look like? Well, if you take this ellipse, because that's what they would look like if you cut them, if you look at them vertically onto, imagine this is your xy plane, can you see that what you make is a circle? And what does that circle look like? It looks like x squared plus y squared plus equals 1. So essentially, they've also told me what d is. And now we're going to take the curl of this guy, and it ends up being this expression here. And do you notice that that z gets turned into y plus 8, so that's why I now have y plus 6 here. So here's our p, here's our q, and here's our r. So step 1, that's the equation of the surface. Step 2, that ends up being what it looks like on the floor, so that's my region D. Step 3, find the curl of this guy in the usual way, and make sure everything's in x's and y's. And then, what's my step 4? No, okay. You're not getting a step 4. But I know what step 4 would be. Don't you just put the whole package together and you are finished? And by putting the whole package together, I mean, this is not this one, but it's a version of it, that guy. And if you do, it's just a boring polynomial with x's and y's in it, and you'll be done. So basically, there's no step 4. Question 5, I skipped. It's very similar. Now moving on to number 6. And we're going to use Stokes' theorem, as always, to get this fella. Here is your vector field. And this one is a little bit weirder, because what they've done is they gave you a picture that looks something like this. And this curve C is given by that parametric equation. So they've definitely hid the equation of the surface, because the surface would be that guy. And not just that guy, but that guy forever. Imagine not the curve part, but everything else as well as the curve part. So it's pretty clear to me it's a plane. And we'll have to figure out what the equation of that plane would be. And this is what I did. The equation of the plane has to be z equals. Right? They're all z equals a function of x and y. Now, since z equals sine t and y is equal to sine t, that means when you put them together, that the natural conclusion then is that z equals y. So we've actually got the equation of the plane that this ellipse would live in. Not just the ellipse itself or the inside of the ellipse, but the entire plane that the ellipse and the curve that's part of it would live in. Now, it gets a bit trickier how I came up with this, but here goes. If you imagine this ellipse, if you look at it vertically above, it causes a shadow on the floor. And what does that shadow look like? Well, you make z 0. And so I'm looking at an x equals cosine t and a y equals sine t. And then I'm trying to figure out what equation using x's and y's has this parametric equation. And the simple thing is if you take x and you square it, and you take y and you square it, it's equal to 1. So that's where the equation of that thing is. And so if you look at this ellipse on the ground, I'm not drawing it, there'd be a circle on the floor. In fact, all ellipses, if you look at them vertically going downwards, are going to look something like a circle. So what do we have? We know the equation of the plane is z equals y. we know that the ground D, which is what this guy is basically just a unit circle. So I can use polar for that. Step 3 is we find the curl, and there's the values for Fy and the Z components. And if you do the usual, cover this guy up, 0 take away 0. In fact, the answer comes out as simply just this guy. So let's continue this one now. This is P, this is Q, and this is R. And we like zeros. And I'm going to write next door to it, Z, which is this fella, XY, is Y. So that's good. And I'll write down what region D is as well. I'm just trying to put everything in one place. So there's D. Right. So if you want to get the equation, then what you need to do is use this fella, which is essentially, there's more than one flavor of Stokes, but this is the version we're using. It's a double integral of D. We're then going to take negative P dg by dx, negative Q dg by dy, plus R dx dy. This is going to be from R equals 0 to 1, from theta equals 0 to 2 pi. Negative P is nothing, so I don't really care what all of that is. It's just going to end up being 0 anyway. Q, same idea, a whole load of zeros, and R is 2x squared, say dx dy. There's a kind of mixture. I shouldn't really have called that until later, but essentially I'm going to do polar. So R equals 0 to R equals 1, theta equals 0 to theta equals 2 pi. X becomes R cos theta squared, and that guy becomes R, in this order, d theta dr. So I'm going to have 0 to 1, 0 to 2 pi, 2 that, and that gets me 2r cubed with a cos squared theta d theta dr. And now I'm going to split it into 2r cubed drs, because it's variable separately, and 0 to 2 pi of cos squared. And so this guy would fit in here, but since I'm running short of room, let's convert it. What do you need to convert cos squared theta into to allow it to be integrated? Because in that format that it is right now, it does not integrate. Any takers? Trig identity cos squared theta equals something, and you need to be able to do a conversion to tell me what it is so I can integrate it. Any takers? Last chance. I'll give you a start now. How about this?
I thought it's a 1/2 times something.
Yeah, it is. It's a 1/2 times something. You want to try and guesstimate the rest of it?
One minus sines, sine squared, cosine. Oh, 2x.
Or theta in this case, but 2 or something. Right, that's the guy. I'm going to leave it at that point. Won't you get this guy is some ugly fraction, this guy is some other ugly fraction, and you multiply them together and bump your uncle. Are we good? Last chance. Any questions on that one?
I'm good.
Okay. I think the only saving grace, because these are long questions, I know I've written things down so they go quicker than they typically would, but the only saving grace is they do have a flow to them, don't they? You kind of do the same thing, right? And most of the time, the shapes that you get on the floor are triangles or bits of circles. And if it's bits of circles, you go polar. And if it's triangles, you keep everything as X's and Y's. Right, so our last one then. We're being asked to find this one. I don't think they said, I'm pretty sure they didn't use Stokes' theorem, but since it's in a Stokes' theorem section, it's obvious that that's what you have to do. And this is the vector field, and this is a curve. So basically, something is passing through this shape, and these 3 points in particular. And you're finding the work done, because very often that's what this evaluates, right? So if you do a line curve passing through a vector field, very often that represents the work done in traveling through that vector field. In this case, you go from here to here to here and back to beginning. So first thing we're going to have to calculate is the equation of the surface, the plane. I know it's a plane because if you pass through 3 points, you make a triangle, and that triangle is embedded in some three-dimensional plane. So I'll call this guy P, this guy Q, and this guy R. And I find the vector joining P to Q, which is this one. I find the vector joining P to R, which is this one. I then find the normal by doing the cross product of these two, and you just trust me that it's this. And then we use the equation of a plane formula, which basically is where this comes from. And so you end up with that. And so Z actually just ends up being 1/4 Y. So the equation of the plane that passes through these 3 points is just Z equals 1/4 Y. So that's step one done. Get the equation of the plane. Now, how about step two? Well, can you imagine this triangular plane floating about in, in a sloping kind of way? And we want to know what it looks like when you take these 3 points and project them onto the floor. And so the way I figure out what that is simply just taking the coordinates of them. And if you want to know where each corner of that triangle would be on the floor, you just make the Z value 0. And so you end up with these 3 points. So 3, 0, 0 gets you this guy, 3, 4, 1 gets you this guy, and 0, 4, 1 gets you that guy, right? Because you make the Z coordinate 0, that's the guy on the floor. Now, when you join these guys up, you do get a triangle. And if you do, as I've decided to go vertical on it, do you see that it's going to go from straight line to here? And the equation of that straight line, if you look at it, 4 by 3 is -4/3 x, and the y-intercept is up here. So that's where the +4 came from. So my region D is starting from x equals 0 and scanning to 3. And each rectangle, the highest part is 4, and the lower part is the equation of the straight line. And so we've got the equation of the plane, check. We've got the region D and its limits of integration that we should use, check. So what we're now entering into is step 3. And step 3 is we are going to find the curl of F. So ijk, the operators, and move this out of the way. Z squared, 2yx, 5y squared. So if I cover this guy up, you get derivative of this guy with respect to y, 10y, take away nothing. Check. If you do the middle one, the derivative of the major is 0 because that has no x's in it. Take away 2z, 0, take away 2z. If you go to the last one, this derivative with respect to x is 2y. This derivative doesn't have any y, so it's 2y take away 0, and that gets you the third one. And then you take care of the little details, 10y minus 2y plus 2y. So at this point, I've decided to take care of the XYZ problem, in particular the Z problem, right here. I know that Z is. We already found Z. He is a quarter Y. So this guy, 2Z, just becomes 2 quarter Ys, and it's just cleaner. Okay, so there's P, Q, and R. 10, P, that guy, Q, this guy, R. Here's our generic formula. You go from x is 0 to x is 3, y equals a straight line to y equals 4. This negative p, which is him, times 0, gone. Negative q, which is this guy, a half y, times the derivative. And if you differentiate to z with respect to y, this guy gets your quarter. If you differentiate this guy with respect to x, that's where the 0 came from, and the r is plus 2y. So that guy is nothing. That guy and that guy get me 15/8y. Pretty standard, usual double integral. According to what I was saying, at least you get 45. That's that section finished.
Can you, sorry, I was
Yes.
writing notes really fast. Can you tell me again how you got the 1/4 y for z?
Sure. But yes. So take all the other distracting stuff out. So we know that it's passing through these 3 points. I'm going to call this guy P, this guy Q, and this guy R. And if you want to find the equation of a line passing through 3 points, imagine that this would represent P, this would represent Q, and let's say this would be R, right? So you end up with a little triangle. But you want to find the equation of the entire plane that this is just part of. What you do is you find PQ and PR.
You're doing the PQ, PR, and then, okay.
And then the cross product, yeah, gets you the guy that's called the normal. And then you have a little formula that says something like this. The normal dot product with XYZ is equal to the normal dot product, the position vector of anybody you like. I'm choosing P. And so if we assume that this guy here is correct, which I'm sure he is, this guy, dot product with XYZ, and this guy, dot product with 300. Well, actually, after all that work, the answer is 0. And this guy, that doesn't matter because it's 0. You get a negative 3y plus a 12z. And it's just a matter of rearranging it and getting it into the z equals format. And you're finished.
Okay.
Right. There was an earlier question where you had 3 points as well. And it's essentially the same process. I just told you what the equation of the plane was just to speed things up. The one I was thinking of is, I think there was one that went 300,030,003. Right, if you did that one, you would find out the equation was x plus y plus z equals 3, and then you'd rearrange it.
Okay.
Okay. Now you're welcome. There's been a number of changes to some of the Project 1 questions. There was 2 that I know of that I recollect. One of them, there was a sine of x squared that was turned into the sine of 2x. And there was another one, if for the life of me, I can't remember where it is, but there was another one somewhere else. Anyway, I fixed them, and the updated version is online in Canvas. So if you haven't reached the later questions, it won't matter, because when you go and look now, it's been fixed. So the problem has disappeared. Thomas, can you remember if there was another one that I just, oh, looks like you've got a comment, so that might be the one I can't remember. Right, so it's 15 and 17. Let me go and look at WebAssign and see if I've fixed both of them or only one of them. 15 and 17, here goes. Takes a few minutes to load up dashboard. Right, once today's finished, I'm going to hang about for any questions that you might have on the project, because I know that some of you asked some questions and it really isn't anything easy to do over email. It's just not possible. There's just too much to type. So I'm almost there. Right, here we go. So let's close this off and stop that share and close this share. Right. So you all know that your project is due midnight Wednesday, hopefully. So when I see you on Wednesday, we have one last section to do. And again, I'll try and do it as efficiently as I can, so that at the end of the lesson, we can have some time to go over any questions that you may have encountered and try and fix them. Okay.